Hello, and welcome to my talk about Managarm, a fully asynchronous operating system powered by modern C++. So, I'm Alexander van der Grinten. First, a bit of info about myself. So I'm a postdoctoral researcher in computer science. I'm currently working in Berlin in Germany, and I've obtained my PhD in 2018. But, well, this is not really about research. My research focuses more on parallel algorithms, graph algorithms, and hard combinatorial problems. But in this talk, I'm actually talking about something entirely different. Namely, I'm talking about Managarm, which is a pragmatic operating system with fully asynchronous I/O. And by pragmatic, I mean that this is not really bleeding edge research or so, but this is really something that we aim to, provide a usable product. It's an open source project. It's not actually funded by my employer. It's founded in 2014, and it has a few active contributors. So this is not only my work, but the work of others too. But now let's get into the topic. So what will we cover in this talk? First, I will discuss why asynchronicity matters in operating systems and also in applications. I will give a brief overview of Managarm. I will discuss how async can be done in C++20, and we will see that there are different mechanisms that should be used for high-level code and for building blocks. Then I will go through the implementation of async syscalls. So these are the basis of the entire operating system, and we will see how they can be implemented in C++20 and how C++ especially is a very powerful tool in this context. At the end of the talk, we will discuss some open challenges and make some conclusions. Good. So now let's get to the first point. Why does asynchronicity matter? And to understand that, I'm actually going to make an example of synchronous I/O. We look at POSIX files. That's well-known technology, and OpenGL. I just picked this example because many probably know these technologies, or at least have heard of that. They are straightforward, they are well understood. And for example, if we want to upload a texture from the file system to the GPU using POSIX and OpenGL, we can do it like this. We have a function that just takes a path. It allocates a constant size buffer, so it allocates 4,000 bytes here on the stack. And then it opens the file, it reads a chunk of data, and uploads that data to the GPU. There's nothing spectacular here. This is pretty standard code. I'm also abstracting away over things like file formats that would play a role in real code here. And I just assume that everything is a bitmap and that this works. So if you look at that code, it's really easy to understand what it does, right? It's synchronous. We can easily reason about all the things that this code does, but it does not really scale well. Why not? Well, these system calls, open, read, and whatever GL text subimage 2D uses internally, they all block the count thread. And you might think, okay, that's maybe not an issue for this code, but it becomes an issue if we suddenly want to read 1,000 files and upload 1,000 files to the GPU. So we cannot just start 1,000 threads and call this function once per thread. That's really inefficient. That just won't work and won't scale very well. And I also claim that these abstractions that we see in this code, they do not really map well to modern hardware. So why is that? I claim that modern hardware is highly asynchronous. And to understand that, we just need to look at the evolution of storage technology. 15 years ago, in 2004, there was SATA, or by its technical name, AHCI. It has one request queue, which means it can process one request at a time and answer one, for example, read or write request at a time. And the OS can post 32 requests to this queue. Afterwards, the queue is full, and the OS needs to wait until the queue is drained again. So far, so good. Now, what happened 10 years later? Well, modern devices, which are called NVMe devices, they support many more concurrent requests. They support thousands of concurrent requests, at least at the higher end of the at least the high-end products to do that. And well, they can also store many more requests per queue before the OS needs to wait until I/O is finished again. So the crucial point now is that if you're writing I/O in a synchronous way, so if you're writing it like we've seen before, then your thread can only post one such request and only to one such queue. It will never post many requests to many queues at the same time, and that's a huge bottleneck. You cannot really utilize this modern storage technology using only one thread, at least not if you're not using async. Good. And the story is similar for other devices, for example, for GPUs, for networking devices at the low end. So if we look at Wi-Fi, but also at the high end, if we look at InfiniBand, they are all asynchronous. They support many concurrent requests, and InfiniBand even supports very deep queues where the kernel, the operating system kernel, is not even involved in moving data around. Similar story holds for accelerators. These will become more important in the future. For example, AI accelerators, crypto accelerators, and so on. And also other well-known technologies, let's say audio or connectivity technologies like USB. And if you sum that up, well, that's almost all that covers almost all device that you find in your PC or in your server, depending on what you're looking at. So, well, if we need asynchronous code to exploit these devices, what can we do? Let's ask the question, what can we do in C++20, right? C++20 is our new technology here. So how can we adapt the code to, well, perform better in an asynchronous environment? And ideally, we want to do this. We just want to replace the void returning function by a function that returns some future, some asynchronous result. So I call that here async task void. And then we replace the synchronous calls by just co-awaits. So we co-await the result of the open call, we co-await the result of the read call, and we co-await the result of the texture upload. So that's our ideal scenario, that we can do everything in a coroutine. And due to the nature of this code, it's equally easy to read as the blocking synchronous code, but it can now actually scale to a large number of threads or a large number of concurrent requests, because you can launch multiple coroutines per thread. We can easily launch thousands of such coroutines without any noticeable overhead. But now, some of you might claim, hey, that just doesn't work that way, right? These abstractions don't exist. The POSIX functions do not support asynchronous behavior. OpenGL does not support asynchronous behavior. So it's not that easy. But, well, why is it not that easy? Because the infrastructure is not there, but we can try to, well, build this infrastructure. And as a side remark, there are technologies like Linux, IOUring, or Vulkan, and they can do these operations on this slide here asynchronously, but they are not a general solution. For example, IOUring often has to fall back to threads in certain cases where the Linux kernel is just not able to perform a operation in an asynchronous way because it was coded in a synchronous way. So there's no free lunch here. Good. Now let's get to Managarm, which tries to avoid these issues by just building on asynchronicity from the ground up. So in Managarm, everything is asynchronous. So we do file I/O asynchronously. That includes metadata updates, which is a problem for existing operating systems that were coded with synchronous I/O in mind. So they often have to do metadata updates in a synchronous fashion. Our drivers are fully asynchronous, so internally we can often use coroutines instead of callbacks. Interrupt processing becomes a lot easier. That's something that we'll see later during this talk. And also stuff like device operations, I/O control in Unix are asynchronous in Managarm. So there's no restriction for asynchronous code here. It also affects memory management, but I don't really want to go into detail here. But if you think about memmap in Linux, that can block in certain circumstances, and it cannot block in Managarm because it's also implemented asynchronously. Good, and all the other stuff that you know already, for example, networking, that's a well-understood problem, of course, that can also be done asynchronously in our new OS. I'll give a high-level overview. So in contrast to existing operating systems like Windows or Linux, Managarm employs a microkernel. So these of you who don't really know anything about kernel design or operating system design, an operating system is usually split into two parts, which is the kernel. That's a privileged program that implements hardware access and provides this access over some safe interface to applications. And then there are user mode applications that, well, run on this kernel and use system calls to call into it. And these system calls follow a well-defined API so that there are no security issues or permission issues. But in Managarm, our drivers also run as normal C++ programs. They don't have supervisor privileges. They basically cannot do everything the kernel can do. Yeah, and therefore they are also much more easier to write. We'll see that in a minute. What does our kernel do? Well, it still has to do memory management, it has to do scheduling, and it has to do IPC. There's just no way around that. And because of these special constraints that, well, it has to do its custom memory allocation, it cannot really use full C++20, at least it cannot use the STL. So it's written in a freestanding subset, whereas the user mode applications are written in just standard C++. We're using an STL-like support library here, which means that many things are actually available in slightly different form, but it's not exactly the STL. Luckily, that part is small because user mode contains almost everything, and that's hardware drivers, all the POSIX code. So we provide the POSIX emulation on top of our native interface, and our applications, of course, also run in user mode. So yeah, the user mode things are written in fully compliant C++20 and have access to the full STL. So even when writing drivers, we can use standard vectors or whatever classes we want to use from the standard library with, well, certain exceptions. For example, you cannot use a file system when you're writing a file system driver, but let's not get into this. What are the features of the OS? So we have some Linux source compatibility, which means we can recompile Linux programs to run on our OS. We cannot really provide ABI compatibility, and that's not a goal because it would just be a lot of work for little gain. So for example, we can also support epoll, we can support eventfd, timerfd, and signalfd. There's a mistake on that slide. We have file systems like dev, proc, and sys that have a similar layout as Linux, and we can run programs like Wayland and X11, desktop programs, yeah, and so on. when I say we can do that, of course, we need to translate between our asynchronous API to Linux blocking API. And that has to happen somewhere. And in our case, it happens in a C library. So the C library sometimes does an asynchronous request and then just blocks for its completion. That's basically the cost of using the emulation layer. For applications that use our native API, this translation obviously doesn't happen. Otherwise, there would be no benefit. By the way, our libc is also written in C++, which might be a nice insight. Okay, what do we support as hardware? We support most virtualized hardware. Virtualization is, of course, important today. And real hardware is work in progress. We support many modern devices, but not nearly all legacy devices. There's just too much to support. The current status is that it's functional. The OS is functional, but it's not really stable, so it's easy to crash it or easy to invoke functions that are not implemented 100% correctly. For example, if you look at proc, it does not have all the proc files that Linux has, but it has only a small fraction. Good. Yeah. I'm going to do a case study here in this talk. So I'm going to look at how async helps in low-level driver code. And for that, I'm going to explain how low-level driver code often works. So we've already seen that hardware is asynchronous, it's highly asynchronous. And how does a driver for such asynchronous hardware work? Let's imagine we want to read something from disk, okay? Then what usually happens is that a driver writes some commands to a buffer in RAM. The layout of the commands, of course, specific to the device. And I'm not going to go into detail here. But then we notify the device using some mechanism that commands are available, and the device starts reading these commands and it performs work. And at the end, the device notifies the driver again. And that happens usually using an interrupt. So what's an interrupt? That's something like a signal handler. It's really just the same as a signal handler. So wherever the CPU currently is, it just starts executing at a different place. It jumps to a different function. And that has all the bad implications that true signal handlers also have, right? They have to be very careful about what they do because, for example, if they take a lock, they must make sure that it just didn't interrupt code that already has the lock. Otherwise, you get a deadlock and stuff like that. You cannot just allocate memory, at least not without ensuring that the memory allocator is not running concurrently in the non-interrupted code. That's all tedious to deal with. And that's where asynchronicity comes into play, because if we can handle the interrupt asynchronously, everything becomes much easier. Traditionally, these are handled by signal handlers or callbacks, but we can use coroutines more or less to handle them, and we'll see more on that later. And because we can use coroutines, it becomes easy to write correct and concurrent drivers. So we don't necessarily have to write parallel drivers here. If we have the right abstractions, it turns out that we can write drivers that can handle many concurrent requests without being parallel. And that takes away a lot of the complexity of traditional drivers. But to illustrate that, maybe let's look at traditional interrupt code. Let's give a brief overview over that. So this is already written in the C++ way. So if you're trying to find that in the Linux kernel, then you're out of luck. The C code is obviously quite a bit more ugly here. But let's assume that we have a standard mutex and a standard DAC that we can use to communicate between an interrupt handler and some other code. Let's imagine this is a driver for some device, let's say a mouse or a keyboard or whatever. Whenever you press a key, you get such an interrupt, and we need to read certain data from the device, and we need to process it. And already here we have to make some assumption, and that assumption is that this interrupt callback, this interrupt handler, is not called reentrantly. So while it runs, we already assume that it cannot be started again, which is something that the CPU actually needs to ensure first. So that's not given for free in reality. But now we automatically have to log. At least if you have a multi-core CPU, we do not know which thread we interrupted, so we have to log because, well, we have to synchronize against code that runs on a different core. After we've done that, we can read some data from the device. Let's say that's done by this dev.getByte function here. And we push the data into the queue. Why do we do that? Well, we do not want to work in this signal context, in this interrupt context, but we want to do the main body of our work outside of this interrupt context. So we use the queue to push data from the interrupt context to some context where it's easier to write correct code, where we don't have to deal with complex reentrancy issues. And in our toy example, let's assume that we need to parse uint16s, right? So the device gives us uint8s, and we need to parse uint16s. Sounds simple. First thing that we need to do is we need to disable interrupts. Why is that? Because we need to ensure that we do not call into the interrupt callback again while we're accessing the mutex. Otherwise, we can get deadlocks. So then we have to add an implicit state machine here because we do not know the size of the queue. If there are more than 2 bytes or 2 or more bytes, then we are fine, and we just retry the operation if that's not the case. How that works is out of scope here, but this is not so far from a real example. Once that's done, we can do real work. We can get data from the queue, we compose it to a word by just, using bit shifts, and then we process the data in some device-specific way, right? And at the end, we re-enable interrupts, which means that the interrupt callback can now be called again, and we can finally continue with other code. So that's what we see here is that as soon as you have signal handlers, or in this case interrupt handlers, you automatically get complex locking, which is really annoying. So let's look at how this works if we can use async. Actually, it becomes much easier. So we replace everything by async data structures. So we use an async queue here. We have now a coroutine which handles interrupts, and that just awaits until an interrupt happens. We have a sequence number that just counts how many interrupts occurred so far. And now this is more or less real code from Managarm. Our syscall API is called helix. So there's a function helix await event, and it just waits until an interrupt happens. When that indeed happens, then we get a byte like before and push it into our async queue. And we take the sequence number of the interrupt to just count how many interrupts occurred so far. And then the consumer becomes also much easier because the queue is now async. We can consume it in a coroutine by just popping data from the queue. We don't need to code our state machine explicitly here. We don't need to care if the queue is empty or not, because we can just wait until the queue is non-empty, and that's how we can process data from the device here. So if we compare the examples here, first of all, the code is more concise, okay? There's no explicit state machine here. The code outside of the interrupt handler does not have to care about the state of the queue here, because it just uses the right abstraction to just pop data. And we remove the need for complex locking because we don't have a signal handler thing anymore, but we can really handle interrupts in a loop because we can wait for the next interrupt to happen. That's just much easier than having a signal handler. Okay. Yeah, questions. There are a few questions in the chat. So what compilers are available on Managarm? So as cross-compilers, GCC and Clang are available. Working on Managarm, I think, is only GCC so far. What STL library are we using? We are using libstd C++, so GCC's standard library. The license is MIT. Do you have a performance comparison of what? Well, I can say something about performance later on in the talk. Okay. Good. Let's continue. And what I'm going to do in the remainder of the talk is I'm going to look at how these async syscalls actually work. So I said that we have this line, helix await event, and it takes an interrupt. It takes a sequence number, so basically a number of an interrupt that we're looking for, and it waits until the interrupt happens in an asynchronous way. And that's in Managarm an asynchronous syscall. Remember, a syscall is just something like open, read, write in Linux, and in Managarm, syscalls are almost all asynchronous. So how does that work? Well, okay. Also, asynchronous syscalls exist for other stuff, like IPC, task management, memory management, and so on. I'm not going to go into detail here. But I want to take a closer look at this mechanism, how the asynchronous syscalls are implemented. So the syscall is invoked by user mode. Remember that all our drivers and so on, they are invoked by user, or they run in user mode. And there is a stub function, which is now called here health submit await event, which initiates the asynchronous operation. Remember that the asynchronous operation is initiated at some point and completes at a later point. Good. It takes a handle to the interrupt as input. It takes a sequence, that's just the sequence from the await event call. And it also takes a ring buffer. We'll get into that later, and a context pointer, which is just an opaque value for the kernel. The kernel doesn't look at this at all. It just passes it through the stack and through the syscall mechanism, and we'll see how it's used later. Good. Then, okay, the syscall has to perform some async work in the kernel, right? In this case, it has to wait until an interrupt happens. But it could wait for other things, like it could wait until an IPC message is sent successfully, or it could wait until enough memory for something is available, or it could wait until a task is in a certain state or so. And then the kernel needs to notify user mode again after the completion of the syscall. So the kernel needs to notify user mode that the work is now done. Obviously, that has to happen somehow. And in this process, there are two layers involved. There's the operating system and there's C++. And I'm going to explain in both layers how the mechanism works. So let's look at the last step, maybe first. The notification. So the kernel has done some work, and it wants to notify user mode again that the work is done. There are different ways to do that. For example, on Linux, there's epoll. A newer mechanism on Linux is IO uring. And Windows has, for example, IO completion ports. If you've done some async programming, you probably know at least one of these technologies. And what we do in Managarm is something similar to IO uring. We use a log-free ring buffer. So the kernel needs to send something to user mode, but it cannot directly call into user mode. It cannot directly, for example, pass a pointer to user mode. That would not be helpful. because kernel pointers live in a different space than user mode pointers. So what it does is it puts an element into a ring buffer and notifies user space using this ring buffer. And that's also similar to how IO uring works. In the best case, that means that we have 0 switches between the kernel and user mode to get these notifications, because if there's already a notification in the ring buffer, then user mode doesn't have to block at all. User mode doesn't have to enter the kernel at all. If there's no notification and user mode wants to block for a notification to appear, well, then it just does that, and that costs us 1 entry in the kernel. And that's actually our only blocking syscall, more or less. We block on an atomic variable. We block until an atomic variable changes. And if you've read the C++20 papers, this has been accepted into the standard as a standard operation. So it was already available on Linux as a futex or as the function wait on address in Windows. And now it's also available as a method of standard atomic data types. So that's basically our only blocking operation that we ever need. And I'm going to illustrate how it works. This is our ring buffer. So in reality, the ring buffer consists of different chunks, but I'm only going to display a single chunk here. The chunk mechanism is just necessary to prevent overflows. So once one chunk is fully utilized, then the next chunk needs to be used. So within such a chunk of the ring buffer, there are elements. Let's just call them elements. These are notifications, right? These are notifications from the kernel to user space that some kind of work has been finished. And how do the kernel and user space communicate here? Well, both store a pointer, and because the kernel is the producer, it stores a pointer that points to the that points past the last element that it wrote, whereas user mode is the consumer, and it stores a pointer past the last element that it consumed already. Okay, which means that both pointers always go to the right because the kernel keeps producing more elements, and the user mode keeps consuming more elements. How's that done in C++? Well, that's there's a bit of log-free programming necessary, but it's not actually too hard. I'm not going to show the code, but I'm going to show the data structures here. So first of all, the chunk needs to be represented by, well, just an atomic integer, more or less, and that into that atomic integer, the kernel stores the its right pointer, just the pointer that's visualized above. And then user mode uses the wait function on this atomic variable to wait until the kernel pushed more data into the chunk. And then it can update its own pointers and read the data from the ring buffer. Each element is delimited by a length. And now here we see that this void pointer, this context reappears, where this opaque value that I mentioned before. So when we initiate the async syscall, we pass a user-defined value to the syscall. And then when the kernel informs us that the syscall is done, we get back this user-defined value. And we can use that, for example, to point to some C++ class, to some C++ object. We'll use that to continue our asynchronous code. So for example, to resume some coroutine or to resume some asynchronous algorithm. And okay, each element also has to store some syscall-specific results, for example, error codes or number of transferred bytes in IPC messages or whatever. All right, that's the OS layer. I'm not going to explain that in more detail here. So now I'm going to look at the C++ layer, because this is a C++ conference and you're more interested in the C++ probably. So how does it work on the C++ layer? We need some representation for async primitives in C++. And such an async primitive is, for example, helix await event. Yeah, so maybe the obvious choice is awaitable. So awaitable is this concept here. It makes the type co-awaitable. And to do that, we have some awaitable object A, and there are three operations: await ready, await suspend, and await resume. It's not actually so important what they do, and I'm not going to explain it because there are probably better talks on how coroutines work. But the crucial point here is that await suspend needs a coroutine handle. That's basically just a coroutine. And that means that if we use this awaitable concept as our building block, then we need to be in a coroutine to wait for the completion of awaitable operations. Okay, because otherwise you cannot get a coroutine handle. And yeah, let's see if that is an issue or not. But in any case, it means that every consumer of async operations needs to be a coroutine. And yeah, we'll see why this is an issue. First of all, I'm not going to bash coroutines here. So coroutines are great. You want to write almost all of your async code in coroutines. My rule of thumb is here that 90% of your async code should be coroutines. Otherwise, you're likely doing something strange. And they work really well for high-level logic. But I'm claiming that they do not work that well for low-level logic. And that's because coroutines have some overheads. So now I'm looking at an example of an async queue. Remember that we've used an async queue before in an example. And now I'm going to look at how we can implement such a popback operation of an async queue. And actually, I'm going to cheat because I'm going to assume that I already have a popback operation that can be canceled. And all that I want to do is construct a popback operation that cannot be canceled. My cancelable operation should return an optional t because, well, in case it is canceled, it just returns nothing. While my non-cancelable operation should return a t, a task t, so an asynchronous result of type t. And how we're going to do that is we have this cancellation token, which somehow controls when the operation is canceled. And we're going to pass a cancellation token that just does nothing to the original function. We're going to co-await the result. Oh, that's something that is broken on this slide. So we want to co-await the popback operation. And then we want to move out the result out of this optional R here. We know that there's a optional value available because well, the cancellation token is never canceled here. So that works and it looks quite simple, but there's an obvious drawback if you dive a bit more into how coroutines work, because coroutines potentially allocate coroutine frames. Not in all cases, so there are great optimizations that can avoid this, but it can happen in certain cases that we need to allocate a coroutine frame. So we need to heap allocate something, and there are certainly situations where we don't want to heap allocate. For example, if we have async algorithms, and we'll take a look at async algorithms in a few minutes, then it's not desirable to make every async algorithm allocatable. So I'm claiming that awaitable is not the right primitive here. And what we're going to do instead in our OS, or what we do in our OS, is we borrow stuff from the executor's proposal. We borrow senders and receivers. These are concepts, and I'll give a brief overview on the next two slides. They are not related to networking despite the name, so please don't be confused about that. And I have to post a disclaimer. So what we do here is an independent implementation. It's not a standards proposal, so there are certain differences, but yet the credit of these ideas is certainly goes to SG1 and not to us. But of course, the credit for bugs still goes to us. Yeah. So what are senders and receivers? We have two concepts per async operation in this context, and I'm going to give the informal definition. So a sender is the first concept. A sender is a class that knows how to initiate an async operation. So it's something like a pre-baked function call. Think of it as a tuple of arguments. So nothing really special. It's just a function, and I know how to invoke the function. Then I have some operation object, and that's just a class that represents the state of an async operation. Okay, and that's something I need to implement for each primitive async operation. And then for each consumer of async operations, I need to implement a receiver. And that's a class that knows how to resume after an async operation completes. So it's basically a callback on steroids and nothing more. So all these three things are really simple conceptually. They just have names that make them sound like, well, make them sound more complicated. At least if you haven't looked at them deeply yet. So more details can be found in David Holman's and Eric Niebler's talk from last year's CPPCon. And if you're interested in these topics, I really advise you to watch that talk. Good. I'm going to explain senders and receivers now in one slide, and hopefully that works. So we have a sender S and we have a receiver R. And we proceed in 3 steps. First of all, we need to construct the operation object. And that happens by calling a method called connect. So it connects a sender and a receiver. So it takes these 2 objects as input and outputs an operation object. Why is that interesting? Usually the sender and receiver are just movable objects. They store some data and they can be moved around, but the operation is something that cannot be moved. And why can't it be moved? Because at some point the operation needs to complete. And for that, we usually need a pointer to the operation. So the pointer must not change. Otherwise, we run into problems. Okay, then this does not really start the operation yet. To start the operation, we call a function called start. That's not really surprising either. And now the operation does some async work. And when it's done, it calls a function called setValue on the receiver and passes some value. Potentially passes some value to the receiver. That's how our callback works, and that's our 3rd step. Good. Yeah, you see, this is really simple. There are a lot of objects involved, and without taking a close look, it might seem a bit complicated, but if you consider these concepts more deeply, they really make a lot of sense. And what does this allow us to do? First of all, it allows us to write 0 overhead async algorithms. So if we go back to the example of the non-cancelable popback, what we can do now is we can write a generic algorithm, let's call it async transform. And what it does, it takes another async operation. So the result of popback, of the cancelable popback, is an async operation. And it just applies a function to its result. So we take the optional t and we move out the value. And that's equivalent to the code that I've shown before, only that it uses an async algorithm, namely async transform, instead of a coroutine. Examples for such algorithms are the transform algorithm above, a sequence algorithm that just calls different async steps one after the other, or an operation raise and cancel, which I call raise and cancel. That basically invokes a lot of async operations, waits until the first one finishes, and then cancels all others. Now, these are useful building blocks, and we've also all seen that we can make use of async data structures. These can also be implemented on top of senders receivers, and for example, async queue, or what is often really useful is async recurring event. So that's basically an event that you can trigger and wait for multiple times. It turns out that this is a really powerful abstraction, similar to a condition variable. So I'm going to take more questions from the chat at this point. How do we install Managarm? Well, at the end of the talk, I will have a link to our GitHub repository, and we have some installation instructions there. You should probably not install it on your hard drive at this point, but feel free to try it out in a virtual machine. How easy would it be to write non-C++ applications based on this kernel API? Well, the kernel API is not written in C++. We cannot pass C++ objects over the kernel boundary, but it's abstracted on, the abstractions on both sides, on the kernel side and on the user mode side, they are written in C++. So you would have to rewrite these abstractions. You would have to rewrite, for example, these senders and receivers here that implement our async syscalls. How easy that is, I guess it depends on your language. I wouldn't try to write applications for that in a language that does not support async very well, because then you're just going to, run into callback hell, because everything is async, and if you don't have the right tools to deal with it, then it becomes really annoying to do that. Good. Very briefly, I'm going to take a look how we can actually write senders and receivers. So far, I've only explained how they work. Let's look at how this looks in practice. Hopefully, I can convince you that it's not too hard, even though a bit of annoying boilerplate is required, let's say. Let's re-implement this function helix await event. We have some general boilerplate here, and that's the implementation of the ring buffer. It's not the implementation of the ring buffer, but it's how the ring buffer notifies us that some work has been done. It's basically an unmovable class async syscall here. And, the first two lines just delete the move operators and copy operators. And then there's only a single virtual function called notify, and we assume that the ring buffer code calls this function when it sees a new element in the ring buffer. Yeah, that's just how our notification mechanism works. And then we need to code some struct to represent the result of our await event function. And how that's done is not really important, but it should probably look at the data from the ring buffer, for example, at errors or whatever sequence numbers that are stored in this ring buffer element. And it should somehow make them accessible to idiomatic C++ code. Okay, let's assume that we have that. Now we want to implement the operation object. Okay, first of all, the operation object is templated on the receiver because there's no type erasure here. The receiver is just some concrete object. Our operation inherits from this async syscall class because that's how our ring buffer code will call into this operation when the ring buffer, notices a new element. We also store the data that we need to start the operation. So we store a handle to the interrupt that we are awaiting. We stored a sequence number because that was part of the previous code too. And we store a handle to the ring buffer. These handles are just, in our implementation, they are just integers. So nothing special here. And we store the receiver. And the receiver, okay, we don't know what kind of type that is. Yeah. And now we need to implement the start function. Okay, the start function is really simple. It just calls the native system call. And yeah, a few minutes ago, we had the question, what about non-C++ code? Well, non-C++ code could use this raw system call. But without the notification mechanism in place, it will become really annoying to use it, because you can start the operation easily, but you cannot easily wait for its completion. And what we pass as this opaque void pointer to the raw system call is this object. And we will arrange the ring buffer code so that it uses this object to invoke our notify function. Okay, so remember that this opaque pointer is passed into the ring buffer, and then the ring buffer sees this object and just calls notify on it. It casts it to a async syscall pointer and calls notify on it. And that's how our execution proceeds here. We invoke the set value function on the receiver. This looks a bit different than in the diagram that I had before, because we are not calling receiver.setValue, but we're using some library function here, but that's just a minor detail. It will invoke receiver.setValue in the end. Good, and we construct the result. We construct the result, and as an ingredient, we just need the element of the ring buffer, and we assume that the result class just takes out all data out of this element, all data that it needs, and that's how it works. Good. So this operation is not really hard to code. The sender is even easier. The sender only stores some of that data. It has a connect function. The connect function is again templated on the receiver, and it constructs an operation object, an await event operation, which should also be templated on the receiver. Actually, I forgot the R here. And then it just passes everything into this operation object that we've seen before. Good. And finally, the function that we actually want to call is just this await event function here, and it constructs a sender. So that's just boilerplate to construct a sender. As I said, there's some annoying boilerplate, but yeah, there's no good way around that, I think. In the end, we have these two classes. We have the operation class and we have the sender class, and they're more or less straightforward to implement. Yeah. And that is how our async syscalls are implemented. Very quickly, the full picture again. So the high-level application code calls into the async syscall wrapper, which is a sender, which enters the kernel side of the syscall. The kernel does some work, and at the end posts an element to the ring buffer. Now the kernel wakes user space, wakes the ring buffer code in user space, and well, that completes the sender, that completes the async syscall, and resumes the high-level coroutine. That's basically how it works. And in all layers of the stack, we're using C++ here. At the kernel boundary, we have to, well, somehow translate to raw pointers, because we can pass objects to the kernel. But yeah, in all other layers, we just use C++ 20 coroutines and senders. Good. I'm going to talk a bit about challenges for 1 minute, and then I get to some final questions. So what are challenges in this model? So I said that we have to modify our senders receivers somehow. Our main modification is that we need synchronous fast paths. We noticed that many operations only need to perform I/O on slow paths. For example, a cache that fetches from disk. It only needs to perform I/O in the slow path. And if we do that with senders and receivers, then we invoke chains of callbacks. We always invoke set value, start, and so on. And that quickly accumulates stack frames and runs out of stack space, especially if you do that in loops. If you call such an async operation in a loop, and it actually invokes its callback synchronously, that's a huge problem. So what we do is we have some additional function that does not cause the receiver to resume control flow, but it just passes a value to it. Let's call that pass value. That's not really such a innovative idea, but it would be great if somehow the executor's proposal could deal with that. And right now, it really cannot. That is the problem if we were to adapt the standards proposal to our code. So another pain point is error handling. Well, C++ solved our async problems, but it didn't really solve our error handling problems. So we would like to use exceptions, but that's not really possible. We're using we're using an expected T class, or at least we want to use it, and we're switching to it from the current handling code. We cannot use exceptions because exceptions are non-deterministic, and that has a lot of problems if you look at side channels or real-time latencies and drivers. We cannot afford that one path is just so much slower than the other path. So performance is not the problem. Predictability is really the problem why we cannot use exceptions. So I'm really hoping for a solution of this problem in future C++ versions. Of course, deterministic exceptions would solve this issue, and that would be great, but it doesn't seem so clear if they will actually, be integrated in a standard or not. Good. Some conclusions. Mainstream OSs don't handle async very well. Very few operations are entirely async, and common fallbacks to blocking code exist in OSs. Designing for async from the ground up is necessary to utilize modern hardware because, we've seen that these hardware devices can handle many concurrent requests. So we need some technology to exploit that. Yeah. C++ 20, on the other hand, is well suited for this async low-level code. Our main tools are coroutines for high-level code, for application logic, for driver logic, kernel logic, and so on. Senders and receivers as building blocks, as zero-overhead abstractions, and async algorithms to compose them in a zero-overhead way. Then, given these tools, it becomes really easy to write async code by default, which is great. Async code is now not harder to write anymore than synchronous code, and there's basically no point to write synchronous code for this OS. As a huge benefit, writing correct and concurrent drivers becomes much easier. And that's really a good takeaway message here. Good. We have a website. I don't want to spend too much words on that, and I want to thank all our contributors, which still fit on the slide. Hopefully not. Hopefully, yeah. Good. Finally, let's look at the last questions. So, does every application effectively have to be C++? Say I want to or need to use Python or C or whatever in user space and perform I/O. Well, we have an emulation of blocking I/O. And you can use that, but of course you're not going to get the benefit of async I/O. So the emulation works, but of course, for example, if you're running a database server or a web server and you want to take advantage of these highly concurrent async I/O operations, then you need to write that in an async language. What's the goal? Is it mostly academic or to replace mainstream OSs. So it's pragmatic, so it's not academic. The goal is not to do some bleeding edge research, but it's meant to be a pragmatic project, for example, for servers that need these async operations. Yeah, and that's basically its goal. Good, I think we've run out of time for questions. So yeah, thank you all for listening, and all right, that concludes the talk.